Okay, so we're trying to find this power series expansion. And I think there is an error in the statement of the problem. I think the limits of integration might be missing for the function f of t. So please double check that because I don't think it's possible without those. I could be wrong on that, but just double check that. So we're trying to find this power series centered at 0. And so really what we're looking for is a Maclaurin series. And with any type of power series, finding a power series expansion, it's good to know some power series expansions of simpler functions. And so that's the approach we're going to take on this one. So instead of trying to tackle f of t directly, we're kind of going to go indirectly. And to start with, let's just look at the arctan of 2x. And what I've done here is I've taken its derivative, because the derivative of arctan of 2x is pretty nice. That's where we get the 2 over 1 plus 4x squared. Do a little bit of manipulation, I can write the denominator as 1 minus the quantity negative 4x squared. Now, if you look at this, this is similar to a power series expansion that we should know, which is 1 over 1 minus x. So all I've done here is I've substituted a slightly different quantity in for x. It's the negative 4x squared. I can use that power series expansion and just plug in the negative 4x squared, which I've done right here, and the 2 carries through. Just distribute by the power of n and bring the 2 into the sum here, we come up with the power series expansion for the derivative of the arctan of 2x, which is what we have right here. And if you use the ratio test, you can show that the radius of convergence for this is going to be absolute value of x less than or equal to 1/2. Now, that was the power series expansion for just the derivative of arctan of 2x. We need to do that for the arctan of 2x. So again, as long as we are picking values of x that are within the radius of convergence, so negative 1/2 to 1/2 on that open interval, we can find the power series expansion for the arctan of 2x, which is what we're showing here in the second line. Just kind of showing the intermediate steps there. Also, something you can think about here too is we're also hitting this with the fundamental thermocalculus. So we integrate our power series in the first line termwise, which is where we come up with this power series here. And notice here, all we've done is we've raised the power of x by 1 and divided by that new power. And I've given, again, the general form of our power series expansion, which is still holding for our absolute value of x less than or equal to 1/2. Now, once we have the power series of the arctan of 2x, it's pretty quick to find the power series expansion of the arctan of 2x divided by x. All that we do now is we take the power series we just found, multiply through by 1 over x, and that means we're just going to cancel out 1 power of x from that power series. And so we come up with a new power series right here on the third line, where again, you notice we went from 2n plus 1 to 2n, which still has the radius of convergence minus 1/2 to 1/2. Now, this is where I think there was an error in the statement of the question. Is in order to integrate this, so we're looking to integrate this power series. And in order to integrate a power series, you need to know its radius of convergence and making sure that you're only integrating for x values within that radius of convergence. And notationally, that's where I think we need to have the limits of integration, which is what I think was missing from the problem. And so really what we're trying to do is we're trying to find the power series expansion for this term, which now, because we're picking x between negative 1/2 and 1/2, we are able to integrate this new thing term-wise, which we just hit it straight through. Again, limits of integration, we get the x, you plug in 0 for t here, everything's going to get wiped out, so the n term disappears from our limits of integration. And we're left with our new power series expansion for this integral here. Now, I've given the general form of this. If you want to find the first 5 terms, 10 terms, whatever, this formula here, the general form will give you those. So you evaluate this at n equals 1 plus, or take the next term with n equals to 1, then n equals to 2, and so forth. And also notice that our radius of convergence is still the same here. It's still going to be for all x such that absolute value of x is less than or equal to 1/2. I didn't show all the steps here. Definitely go through and try to work out each step on this one. And I'm pretty sure that's our answer. That this was a really tough problem. So kudos for working on stuff like this.